Good morning. How are you today? Okay. Still alive after I don't know how many days of lectures, exercises, excursions. Right. So I thought we'd start a little bit by some whiteboard discussion. I think I mentioned in the very first lecture that there is something called, I don't know if I mentioned the name, Barendrecht cube, or pure type systems. So in the area of dependent type theory, there are a number of well-known systems. So for example, before there were dependent types, back in 1935, 40 something, Church invented the simply typed lambda calculus. And then, with Curry-Howard, it was invented dependent types. So somehow here is, so I have sort of X, Y, Z here too. So X is simple versus dependent types. And so for example, you by introducing the Curry-Howard isomorphism for quantifiers, you get the notion of dependent types, and you get a number of dependent type system by moving one step along the x-axis. There is also the dimension of impredicativity, predicative versus impredicative. So at about the same time as the dependent type systems were invented by Howard et al. That I mentioned in the beginning, there was also something called System F of Girard, which is a kind of Curry-Howard interpretation of so-called second-order logic. This is a very famous system that if you work in the area of type systems that you often will hear about. It's a system where you can encode data types by so-called impredicative quantification. So there is a type of Church numerals which you can use for natural numbers. There is the dimension of higher order, sort of first order versus higher order. So there is a version of system F which corresponds to higher order logic. This corresponds to second order impredicative logic, and this is higher order logic called F omega. It's also due to Girard. And the most powerful corner is where you have the calculus of constructions. What Koch was before it had inductive types. Yeah. Do you in Sweden? I think we usually draw Y on.
I think Y and Z are switched.
Oh yeah. Thank you. Yes. Right, and so Barendrecht discovered that all these systems could be classified elegantly by what kind of function spaces could be built. There were somehow something analogous to being a type and something analogous to being the type of sets which we have in Agda. And depending on what you are allowed to do when you build function spaces, dependent function spaces, you get greater or smaller generality. And the story behind the calculus of construction was somehow something like the following. There was already Martin-Lev type theory with this limited number of type formers, set formers that I showed you last time. but it was obvious that in order to get a good programming system, we somehow needed to explain what an inductive type was more generally. We wanted at least the same power as in functional programming languages, where you can define your own recursive data types, as it were. And the clever idea that Thierry Coquin and Gérard Huet was that if you combined the ability to define data types by impredicative encodings, like encoding natural numbers as church numerals, which can be done in general. You can encode lists and various kinds of trees, etc., etc. And with type dependency, you can also encode kind of inductive families, like, for example, the identity type, a so-called Leibniz identity. So the idea of them was that by combining dependent types and impredicative quantification, we would get a system which once and for all would solve the problem of what it means to be an inductive type. I remember a memorable occasion when we started the types project. There was a discussion between Gérard Huet and Bengt Nordström, my senior colleague in Gothenburg. And Gérard asked Bengt, well, in Martin-Löf type theory, what do you do when you want a new type? And Bengt said something like, well, we think hard about it. We look at the introduction rules, and then we look at the we try to find an elimination rule, and then we try to somehow think, does this fit Martin-Löf's meaning explanations? And then Gérard, he said, aha, so it's a social process. And Bengt said, yes, it's a social process. And then Gérard said, well, with the calculus of constructions, we had one social process, and that was when we discussed with Gérard whether this system was consistent. So it seemed like a wonderful idea. The problem was that in practice it didn't solve the problem, because although you can encode the church numerals, you cannot derive the induction principle. So in the pure calculus of constructions, when they worked with natural numbers encoded as church numerals, they had to assume the induction principle. So actually doing that, is not much better than somehow, spelling out the induction principle yourself. So instead, somehow the calculus of constructions kind of became the calculus of inductive constructions. And Martin-Löf type theory became Martin-Löf type theory, ITT, with inductive definitions and inductive recursive definitions. So this cube only explains the very core of type dependency with function types. But the type theories behind Koch and Agda are both, some basic idea of dependently typed lambda calculus with the possibility of adding inductive definitions of various kinds. And there was a process, as I said last time, beginning with the work of Constable and Mendler in the New Pearl group, and then gradually understanding more and more of the theory of inductive definitions. And I would say that this process is still going on, because, well, maybe I will explain to you, maybe this point here is somehow the ultimate point of what we understand rather completely. It's somehow when we have all of these, we have inductive recursive families with generalized inductive definitions. So yesterday I showed you Martin-Löf type theory, and I showed you somehow the different type constructors, set constructors that you have in Martin-Löf type theory. And they kind of illustrate, there are special instances of, these kind of dimensions. So down here we have natural numbers. It's an ordinary inductive definition. It's not a family. It's not inductive recursive. And then we had the W type. That was a generalized inductive definition. So it's over here. And then in addition, there is yet another dimension, which is parametrization. So many of the types in Martin-Löf type theory are parameterized, like, you know, it's W of A and B for, you know, what I explained to you yesterday about index type for the branching types. So there was the W type. If we move in the direction of inductive family, there is only one inductive family in original Martin-Löf type theory, and that's the identity type. So it's when you move along the y-axis. It's not generalized. And then we have inductive recursive definitions. The one example of that we have in original Martin-Löf type theory, which is the universe a la Tarski. It comes up here. Why is it there and not there? Do you remember what the constructors look like? Well, the reason is that the constructor for pi and sigma have function types in them. So that's why it's a generalized rather than an ordinary inductive definition. So, so this is original Martin-Löf type theory. So today I will continue and show you a menagerie. Is that how you pronounce it? Menagerie. I don't know, someone French. Of inductive and inductive recursive and inductive families, which can be somehow placed within this cube. And you know, I explained to you also that this cube can be, you know, what it means to be a correct inductive recursive family can be made precise by a schema. And I explained to you how this is, you know, in some sense, something you do by making various modest generalizations of the rules for the W type. You know, what I somewhat messily wrote on that board over there. So, for example, you know, I will have various things. Maybe I will be able to. Maybe I should draw the cube in another place because I will now show them. But among other things, today I will not show this corner, but tomorrow. And up here we will have something like logical relations for dependent types. So Amal showed you yesterday logical relations for the ordinary simply typed, simply typed lambda calculus. And what is interesting is that when you generalize this notion so that you can do similar proofs about dependent type theories, then the logical relations become inductive recursive. And since it's a relation, it's a family of types, so you move in along the y-axis as well. So that's somehow the most general corner, you know, where you have all of this going on at the same time. I mentioned. So Amal said, you know, that probably what she did on the board could be formalized in Koch, and just for the record, it can be done in Agda too. So let me turn on the computer. Let's see if we can remember what it was we're going to press here. Yes, and Would you like to use the projector? Yes. Oh, yeah. Good. And I should turn on my... Right, and then we should... Yeah. So, while it gets ready, I should say to you, that in the directories that I make available on my web page, there are the directories called itype, which contains examples of inductive types. There is the directory ifam, which contains examples of inductive families. And there is the directory IR, which contains examples of inductive recursive definitions. And then there is also the thing I will show you tomorrow called the directory semantics. And including an IR fam, an inductive recursive family. Yeah, by the way, I should say that it's actually perhaps interesting to ask, is there anything beyond this cube? Does this completely exhaust what we can do in intuitionistic type theory? Is that furthermost, topmost point, is that the ultimate point? Or is there anything beyond that? What do you think? There is never an end. No, exactly. It's like when my little girl learned to count, we very slowly went up to 99, and then she said, "Is that the largest number?" So I thought she would become a mathematician, but she didn't. Yeah, so here you see the directories ifam, IR, itype. So lambda structure unfinished, I didn't mean to give you, but it got into the tarball, so you can finish it yourself. Lists without the duplicates, you can finish it yourself. Right. So if we look, for example, optimistically, I had hoped to be able to go through all these examples, because each of these examples, they make some point. So, for example, among the inductive types, there are lots of fairly interesting things there, but I think I will, let's see. I think instead of going into each file, so Booleans, I'm sure you're very familiar with. Brouwer ordinals, in that file, it's sort of like a special, I talked about that when you have, it's like natural numbers with a third constructor, which makes it possible to do something which intuitively is limits of sequences, of infinite sequences of natural numbers, and then you get some kind of constructive notion of ordinal number. Lists, I'm sure you're very familiar with, and the only thing I wanted to tell you about there is, I will just very briefly, I won't even go into it, but list P, that file just shows that there is a parameterized notion of module. So not only can you make the type of lists parametric in the type of the elements, but you can make the whole module which defines lists and various auxiliary functions parametric on, for example, the type of the elements. And you can see what the syntax for that is. If I have some time over, which I suspect I won't be able to, I may go into a little bit more of the detail, but I think you can probably read these for yourself if you're interested. So maybe that one I should show you. Negative data. Oh, I see. So cancel. Oh, I just asked the question whether there was something, something beyond the top corner. We didn't get an answer. Oh, yes, we got an answer. The answer is no. there are other things. What are there? What's beyond that cube? So the answer was correct. There is never an end. But that's a meta argument. Is there something specific that's beyond that cube? Well, so if you paid attention to Bob here, I know that he talked about something which is beyond that cube.
Higher inductive types?
Yeah. So higher inductive type is an extension of what's in that cube. But I would say that the theory of higher inductive types is not yet fixed. It's a topic of research. One knows special examples of higher inductive types, but the general notion, the general syntax and semantics of higher inductive types is still a topic of research. Something else? Maybe at least those of you who already have some exposure to this field have heard about inductive types. So that's yet another generalization which I won't go into. There is a very nice PhD thesis written in Swansea by Fredrik Nordvall Forsberg, which explores the so-called inductive types. That's also something which goes beyond that cube. And then there is yet another dimension, is that in that top corner, I will show you that you can do things which, are very, very, very big universes, very sort of powerful generalizations of the notion of universes corresponding to certain things which have been invented in ordinary set theory. There is something called a Marlow cardinal, and there is also something called a Marlow universe, which fits into that picture. So, my collaborator on the work on inductive recursive definitions, Anton Zetzer, who is originally a proof theorist turned a computer scientist, he has gone beyond this and done even larger things than Marlow universes. He has something called autonomous Marlow universes and pi3 reflecting universe, but they are also they are unpublished, but yeah, they are also beyond. So things go beyond that cube, but for all practical purposes, this cube seems to exhaust what you want to do in practice. Yeah, so here I wanted to show you this, that of course you are not allowed to do things like, introduce a data type saying that, lambda f is in the data type called big lambda if f is a function from lambda to lambda. That's a typical example of something which doesn't result in a well-founded type. If you have a data type like that, you can somehow mimic what you can do in the untyped lambda calculus, and you can get non-terminating functions. And this data type itself is not intuitively well-founded. You should think of all data types, including universes, in type theory as infinitely branching, well-founded trees, so that each branch you go down will eventually stop. And I also wanted to show you the trick. If you want to use, this is the sort of thing that you can do in ordinary functional languages, Haskell and ML. If you want to use Agda as an interface for writing ML or Haskell style programs, you just turn off, and this is the syntax: options, no positivity check, option, no termination check, and then you can write general recursive functions. Of course, you shouldn't put these non-terminating functions in the type because the type checking won't work, but you can do that. And I am sometimes using that because I simply like the Agda interface very much, so I like to do general recursive functional programming even in Agda. Okay, so that's what I wanted to tell you about that. Let's go back. I see this was not. What was I going to? Oh, I was going to show you the. Yeah, so I think I will come back to these inductive types, but one actually inductive recursive type that we introduced yesterday, I think I want to talk a little bit more about, and that is, I explained to you about how you could somehow build the whole constructive analog of the whole cumulative hierarchy of sets on which classical set theory is based, just as a data type in type theory. So so it's this definition. Yes, I should maybe enlarge it. So it's what I showed you yesterday, that it's a W type where the index for the branching type is the universe. That means that you can use any small type, any small set in the universe as a branching type. That is, everything you can define in type theory, you can use as a branching type. So it's very easy to define things with arbitrary branching, sort of uncountable branching even, right? So an element, of this data type, it's a possibly infinitely branching tree. So if there are any adherents who believe in classical set theory, I hope to put this belief in question, because once you see how they are concretely defined, So here, a set is such a well-founded tree. It's a relative to red-black trees and B trees or something like that, except of course that those have only finite branching, so they're only built up by constructors, if you wish. Here we have things which are infinitely branching. That does of course not mean that we need to have infinite computers, but it means that we have inside them we have programs computing subtrees. So they can be very compactly represented, right? Because for a certain natural number, for example, you will compute a subtree. So there are very concrete things in the computer, but they simulate the idea of a set of sets that ordinary classical set theory is built on. But as we know, us computer scientists, a set, although a set is like a list, or more generally like a tree, we should not consider repetitions of elements as significant, and we should not consider order of elements as significant. So the way we do it here is that we don't try to remove duplicates, we don't try to order them in any particular way, but we have a definition of equality which is insensitive to such things. And what is quite interesting here is that this equality is exactly the definition that people in process algebra invented to decide whether two processes, in some process algebra for a concurrent language, maybe you heard about CCS, Calculus of Communicating Systems, by Robin Milner. Such processes were also such possibly infinitely branching trees, and one wanted to know when two processes were somehow equivalent in some sense. One called it bisimilar. So what does it mean that two such infinite trees are equal? Well, it means maybe we should draw a picture here. There. Here is, say, I don't know, something like that, and here is something else. And if we draw them as trees, they will be like this. So why do we consider these two things the same set? Well, it is because there is a function which for each element here picks out a similar element there. So it takes this to this, it takes that to that, and it takes that to that. And of course then, to show that those two are similar, we need to put this to this and this to that. And this is exactly what this long type says, that there exists a function, f. Now I'm going to use Zina's beautiful pointer and save my fragile tendons. So there exists a function f, it's this one, which goes from, in this case, these are 3-element types, such that if you take an index here, for example, index, second index here, and you compare it to the target of f, which is that one, then you get something which is similar. V of I is the set at that index. And they only have to be similar, not equal, because, in this case, they are not equal, but they are similar, bisimilar. And then we need to go in the opposite direction as well, like that. And I could have, put in a redundant element here as well, and we have the same situation. So this is what it means for two sets to be equal, two so-called iterative sets. Yeah, maybe I should write that name down because it's a good term. Right. So these sets is a typical example of what we call a setoid in type theory. Am I writing too low down for the camera? Not yet, okay. Shout. Setoid equals set plus equivalence relation. Power set is not an operation of type theory. So we can't form quotients by equivalence classes as in set theory. But so instead we have to somehow work with explicit pairs of sets and equivalence relations on them. And this is absolutely essential for developing constructive mathematics and programming. It comes very early in the development of mathematics. For example, if you think about how to define the integers, it's possible to do that so that you have a unique representation of each integer. So if you think of two copies of the natural numbers for the positive and the negative ones, and 0, but perhaps that is not the most convenient representation. The one that we informally use for, in our writing is something where we have plus, we call it plus minus 0, right? So it's actually a redundant representation of 0, two elements for it. Or the ones which is perhaps often used in mathematics, that integers are actually formal pairs of natural numbers. But then, of course, there are several representations for each integer, so we need to specify that equivalence relation. So the inconvenience of working with setoids is, of course, an obstacle to the development of mathematics in this type theoretic style, I would say. And again, this is something which homotopy type theory tries to address by doing this in a systematic way, and not only for equivalence relations, but for higher notions of equivalence. Anyway, so, when we define this notion of equality of iterative sets, we have to show that it is an equivalence relation. So we have to prove that it is reflexive, symmetric, and transitive. And when you do that, you think, oh, I so wish I had LTAC. You see, because even these kind of simple things. Well, so reflexivity is not at all too bad. Symmetry is really easy. But transitivity, it just requires that you don't do it too late at night. It's a little bit of an ordeal. So I wish we had LTAC. But let's see, what does Agda have? There, I want to finish the comment. Let me comment out the definition that I painstakingly wrote with my old brain. Let's use Control C, Control A. Oh, he did it. I was surprised. I'm not sure that it discovered the same proof as me. Actually, I didn't check that. So we don't have LTAC in Agda, but we have Control C, Control A. And of course, it's even better than LTAC in the sense that you don't need to think at all. You don't even need to write ring or intros or induction blah or something like that. You just use Control C, Control A, so you can do it very late at night. Unfortunately, so I tried to. I was positively surprised by this. Oh God, it's Control C, Control A. It's really, really clever. But of course, it depends on the situation. I had another definition of bisimilarity, and it couldn't do this. But it can do search if it's not too deep. So it's worth, it's time saving. But of course, it's more somehow good for your physique if you do it in your head. But at least it saves some trouble in working with Agda. Yeah, so I don't know. I think there are so many things I want to tell you. So I won't sort of step you through these proofs, but they are good exercises in Agda programming, doing something which is, well, is it trivial or not? Well, intuitively these proofs are really rather easy once you somehow understand how you need to go back and forth between trees, right? If you prove transitivity of trees, you have to somehow compose these kind of functions. And it seems pretty obvious that if you have two such, they're sort of like isomorphisms, right? If you have two such isomorphisms that you can compose them and get a new isomorphism. It's intuitively pretty clear. But Agda is not artificial intelligence, so you have to tell it in detail why that is so. And it's all this stuff, right, that does that completely rigorously formally as proof objects. And in this case, the proof objects are actually doing something. They're not just elements of a one-element type, as is sometimes the case of proof objects. Here they are really functions that do something. Yeah, so let me continue and show you a little bit more of the development of constructive set theory. Because after you have decided what it means for two sets to be equal, now you can define what it means for one iterative set to be a member of another one. When you formulate classical set theory on top of first order logic, it's a theory with only only one function symbol beyond equality. So it's predicate logic with equality plus the symbol of belongingness. And then all the other axioms can be formulated without any further function symbols. But at least you have to define, when you do this somehow model of a constructive set theory, you need to define what it means for something to belong to another thing. So what you do then, is that you say that the element, the set, the tree U, belongs to the tree sup AV. This is the tree I should show a picture again. So sup AV is the tree containing the VI the VI, Vj for each ij in the index set T of A, the small set coded by little a. So that U is a member of this tree means that there exists an I such that U is equal or bisimilar to V of I. So U belongs to this set if and only if you can find an I such that U is equal to V of I, right? Seems reasonable, right? Seems very clear, right? Seems much clearer than what all your teachers of set theory told you, all those woolly things about Platonic universes and so on, and sets existing, infinite sets existing in infinite universes and so on. This is the real stuff, right? No question.
So a little while ago you said there was no power set construction in type theory?
Yes.
What's the difference between a power set construction and a function from that set into Boolean?
So it's somehow the decidable power set, right? Because Booleans, you think of functions into Booleans as decidable properties. So you can have somehow that sort of power set. What so you mean this, right? A to bool, which also could be written 2 to the A, right? This is a set. And of course, in classical mathematics, the Booleans represent the truth values, the propositions. A proposition is always true or false. So, if you write, in set theory, you write those kind of things, but you don't distinguish between bool and, we very conscientiously distinguish between bool and set, but of course, this identification is at the heart of the classical conception of mathematics. Yeah, good question. More questions? Yeah?
Explain, please, how kinds of Haskell correlate to universes and sets?
No. We can talk about it in the break, I think, because I could maybe say something, or you could maybe tell me something about this. So Haskell has been moving in the direction of type theory. So there are in particular the generalized algebraic data types, which is the Haskell version of inductive families. And I think there is a there is a desire to do more things, but maybe you should tell me what is the latest news about universes and kinds and stuff in Haskell. Right, yeah, anyway, so I shouldn't spend all my time on this, but I think you agreed with me that we have now defined what it means for an element, a set to be a member of another set. But, we are not done because, that is the sort of horror of setoid mathematics, is that everything you define has to be shown to preserve equality. And it's not, as long as equality is just the identity type, as long as it's somehow just equality of representation, then it's preserved by the nature of things. Because, of course, the identity types is the thing which preserve everything. It's, that's what it means to be identical. But when it's a non-trivial equivalence relation, this is not clear. So we need to show that this relation between sets is preserved in both the first and the second arguments. So if U is equal to U prime and U prime is in V, then U should be also in V. And similarly if V is equal to V prime and U is in V prime, then U is in V. And also here there are little proofs that prove this. It's also somehow, if you look at the trees, you will soon sort of say, yes, it's obvious. And this is Agda's version of obvious. Yeah, and this is fun. I think it's my idea of fun. So now, for example, you can define you can define the empty set as, well, the empty tree, or the tree, depending on how you see it. It's there are no, if you think of this as the root, there are no subtrees. There's just a root. The branching type is N0, which was the code for the empty type. So it's a tree with only a leaf in it, right? And in set theory, one would say, the axiom for empty set in set theory would say, there exists a set X such that for all V does not belong to X. This is how you express it without introducing a new function symbol. But of course, it's better to introduce a function symbol for it, a constant empty set here. And then it looks like that. And here you see an example of, this may, God, I'm going so slowly, but this, let me do this. Because it's a little bit instructive to show Agda's empty patterns. So you see here that when we prove this, I have already done the pattern matching of proofs that V is in another set. It means, that there is an index in that set such that V is equal to it. P is that proof. So now intuitively, right, A is an element of N0. So A doesn't exist, And if we try to do pattern matching on A, Control C, Control, you see Agda discovers that there is no such thing. And this is signified by this symbol here saying that, impossible case. And the reason why I wanted to show you this, is that it's a case where the impossible case is kind of embedded. It's a kind of inner pattern. So this is what happens in non-trivial cases, right? So interestingly, or I don't know, interestingly. Let me see what Otto thinks about this proof. It discovered another one. He just said, and the reason is that if this is in the empty set, of course it is in the empty set. It's just like lambda xx is, is a function between empty sets. Right. Yeah, and you can go on and develop the other constructions of set theory corresponding to the other axioms. You can take the union of two sets, for example. You can do, I won't go into detail, but it is, it's quite fun. You can define the natural numbers. You can define a singleton set like that. It's got one element containing only one subtree, which is the thing in there. You can define 0, as one does in set theory, as the empty set, and successor in this, I think for Neumann way, right? So X union singleton X is the successor of X. And then you can define the first infinite ordinal, as one says. It's the set, So omega, has infinite branching, one for each natural number. So here is the empty set. Here is 1, 2, 3, 4, etc. And of course, 1 is itself the set of the empty set, and this is containing 0 and 1 here. 2. It contains this and that. Something like that, right? So it's actually an infinite. It's an infinite but well-founded tree. And this is how it's represented very compactly. You build it by recursion, saying that the first subtree is the empty set, and then the next subtree is obtained from the previous by the successor operation on these sets. So it's all very satisfactory to somehow program up things that you see in the early chapters of a little book on set theory. Yeah, so, yeah, I don't know. You can build bigger ordinals, and you can sort of go on with this game and build bigger and bigger and bigger and bigger ordinals. I think I will stop there with this game, and I will go back to the more pedestrian inductive types. So let's see, is there something else I wanted to show you? Well, maybe I should show you this. I think is quite an important point to be made. You know, with Agda's pattern matching, you go beyond ordinary primitive and structural recursion, which is sort of officially defined by you are only allowed to do somehow structural induction in one argument at a time. But Agda lets you do it simultaneously in several arguments. So for example, it's easy to define equality of natural numbers by pattern matching on both arguments, you know. So this is not literally the way you write it in primitive recursion, because then you have to re-express it by doing recursion in one argument at a time. But luckily, you know, of course, this makes a lot of things more convenient, including the definition of bisimilarity. It also used the simultaneous matching in both arguments. So it will be a little bit of a job to reduce it to ordinary primitive structural recursion. Yeah, and similarly, you know, ordinary primitive structural recursion only allows to somehow analyze one constructor at a time. So you should, in a primitive recursion, you define f of successor of n in terms of f of n. But here, you know, you can pattern match on several constructors, and as long as the right-hand side is structurally smaller than the left-hand side, Agda will recognize it as correct, although it would be a certain job to reduce it to official primitive recursion. So for example, you know, Fibonacci, you can define like that inefficiently. But it's a matching of on depth too. And it is a topic of current interest to generalize the termination checker in Agda. Okay, let's see, what should I say about inductive families? There are also some, you know, in the files here, some very basic examples of inductive families, but I think they are pretty understandable. The example of simultaneously defining even and odd numbers, it's, you know, it's an inductive family in the sense that you simultaneously define two things. It could be indexed by Booleans, right? Even being somehow the thing for true and odd for false. But you can also write two separate, yeah, maybe I should show you to you. Yeah, so here I show how it's done as an inductive family indexed by Booleans. But you can also, you see, you can also define it as a mutual inductive definition, and then you have to write the keyword mutual, and you have to, you know, do some indentation here to so that Agda recognizes that this is a mutual block. Yeah, but I'm sure you can somehow read this, and this is somehow what's within what you can write within, write in Agda, which is somehow good inductive family. Right. It's defined that they are defined at the same time, so the definition of the one refers to the other, and of the other refers to one. Yeah, like it's sometimes called simultaneous. You know, you also have the same phenomenon with when you define functions, like in Haskell, right? Two functions are defined at the same times, but they refer to each other. So you can do the same for data types. Right. Yeah, so the type of finite sets is just about the simplest inductive family that you can define. You know, so that fin n is somehow the set of the n first natural numbers intuitively. The other standard example is the type of lists of a certain length or vectors of a certain length. This is always what is somehow, often what is shown as the first example of an inductive family. And you show how you can type certain functions like the zip function in a nice way because it has some restrictions on the length of the lists that you work on. But this is a little bit more interesting, I think. Because here we discuss a point in principle. Yeah, so when I first encountered type theory, and I heard that it was a language where all programs terminated, this was, of course, a bit of a shock because I had never seen anything like it. I had actually programmed in a number of, by now, rather old-fashioned languages like Lisp and Algol 68 and Algol 60 and COBOL and so on. And it was, of course, always possible to write looping program. And the idea that you could have a programming language where all programs terminate, it seemed at the time very odd and revolutionary to me. And of course, it is a kind of restriction because you are used to write general recursive things. And first example you encounter where this is a problem is to simply write the division algorithm. So it's not only that IDA doesn't recognize it as terminating, it isn't terminating for all arguments, right? It is, you can't divide by 0. So IGDA doesn't accept this, and the only reason why it's blue and green and black is because we have turned off the termination check. But it's not within, you can't reason about it within the official logic of IGDA. So what do you do? So this is something which, type theorists have deliberated on ever since the beginning, the early days of type theory. What do we do in these situations? Obviously, we must be able to treat these kind of functions. So I just wanted to show you a rather elegant way of dealing with it type theoretically called the Bove-Capretta method. What you do is that you define the domain of definition. So, so this is the Euclidean division algorithm by repeated subtraction. So you can, mechanically, if you wish, write an inductive family which inductively generates the arguments for which the division algorithm terminates. So if m is less than n, then if you divide m by n, then the result is 0. So then the pair mn is a pair where which division is defined for. And the successor case says that, well, we reduce m, m divides n to m minus n divides n. So if it's well defined what m minus n divided by n is, then it must also be well defined what m divided by n is, right? So here, but these are all the cases. They reflect the definition of division that I showed you above. That, right? You see that. Still working? Good. Yeah. Right, so we define the domain of definition, and now we can write a new definition of division which computationally works in the same way as the old one, but it has a third argument, the witness, which verifies that this is an argument for which division terminates. So here, this is the 0 case where m is less than n. Then we have a proof for the 0 case. And then we should return 0. And here we have a proof for the successor case. Yeah, the case where, we get the successor of the quotient from the previous quotient. So you see here, that this somehow computes in the same way. So in this way, we can at least internalize first order general recursive algorithms. It's more complicated with higher order. So another possibility of reasoning about this division function is to simply use, instead of defining a binary function, we define a ternary relation, a relation between, the enumerator and denominator and quotient. Just like one does in Prolog, if you're familiar with Prolog programming. And now, we can reason about it in type theory. The drawback of this is, of course, that we can't execute it with Agda's internal normalization mechanism. We would have to have some other mechanism. But this is analogous to what one often does. Well, for example, in Adam's example, we have computation devices which are modeled as some kind of relation, so that it's not that they are computed by Agda's normalization, but if they are computed, they're computed by something external. So it's somehow the modeling step is different from when it's actually Agda's own native programs that are computed. Any questions on that? Yeah?
So if you wanted to execute give BC, would the strategy be to do something like show that the D relation is decidable?
Yeah. Yes, that would be one possible strategy. Yeah, I think somehow your objection is that, well, I guess the natural question is, how do we get these witnesses right? Yeah, I think there is a little story to be told there, and you're right that if this is decidable, then we can compute these witnesses, right? Otherwise, they would somehow have to be God-given. So what one could say, perhaps, is that, when you execute the ordinary program anyway, it's just the step to the Agda representation, which is done in this way. And in a sense, perhaps one could argue that this is a little closer to the original program than this representation is. But it's not a very convincing argument, I think. Right, okay. Induction recursion. This is what I promised Bob to talk about. So let me first take this example. If you use the Bove-Capretta method, well, this is actually the Capretta part of the Bove method. If you do make things a little bit more difficult for you, so you have a nested recursive function, like the famous McCarthy 91 function, which was, invented by John McCarthy sometime far back in the history of computing as a function which is rather difficult to reason about, especially automatically. It's a function which returns 91 for all arguments up to 100 and then n minus 10. So it's obtained by if n is less than 100, then you call the function itself, you increase the n by 11, you call the function on itself, and then you call the function on the result of that computation. If you try to apply the Capretta method so that you define the domain first and then the somehow extended version of the function which has an extra argument which is a proof of the termination of the function, then you see that in the definition of the termination domain you have to call the function itself. So in order to know, that in the case of n less than 100, when, this terminates if the first function call terminates, that is n plus 11, is in the termination domain, and the result of the McCarthy 91 function on n plus 11, if that is also in the termination domain, then the function terminates for this argument. Yeah, I turned off the termination checker, but it's only because it would be impressive if Agda's termination checker recognized this, right? But if I commented this out, then the lower thing Agda would be happy with, right? So you see here we have this phenomenon which we call induction recursion, which is that you simultaneously define an inductive type and a function which is defined by induction, by structural induction on that type. And in this case it's an inductive family and a function on that inductive family. So I think this is a nice example which somehow induction recursion arises naturally. Of course, you could avoid it. You could also do this in a relational style, just define the relation between inputs and outputs of the McCarthy 91 function, and then it's not so mysterious. You just have some kind of relation composition going on here, right? Yeah?
This approach is somehow unsatisfying to the same way that the previous question hinted at, because none of this really shows this function terminates.
Yeah, I agree with what you're saying. And I agree with what you're saying. And it's type theory's attempts to get as far as possible with reasoning about general recursive programs. There is another whole way of reasoning, which is simply that you take a logic which can reason about general recursive programs, And this is a very, it's another approach, but it's somehow outside. Yeah, it's outside the pure framework of type theory. So I will perhaps talk a little bit more about that tomorrow, because it's a little bit related to what I'm going to talk about tomorrow about the semantics of type theory. Okay. I think, that I will leave it to yourself to look at how you can define sorted lists by induction recursion. This is more the sort of example where you obviously don't need induction recursion, but that you get a little bit of a cute alternative definition by simultaneously defining sorted lists and the head of sorted lists. So, in the cube, this is an example of of an inductive recursive definition, which is just ordinary, and so it's not a family, it's not generalized. So it's somehow the corner in the cube right above NAT. So we see that it's actually also inhabited by interesting things. The McCarthy, the Capretta rendering of McCarthy is in the family, it's not generalized, but it's in the family corner, family and inductive recursive corner. So the one which is, there. I think you can figure it out. Okay, but let me instead show you. Yes? Yes, they are always non-empty. That's the way. Yes, otherwise we can't define the head function. That was the reason why they are non-empty. We could, of course, add that also empty lists are. But if we want to define the head function as a total function simultaneously, then they have to be non-empty. Yes, it's always, questions are always good. They always somehow makes it possible to make a point. Or show some embarrassing lack of insight. Yes. I type checked, yes. Even this, even large cardinals type checked. Yeah, so I promised someone yesterday to bring some order in the confusion of universes in type theory, because it is a little bit confusing. So when I explained the logical framework, I said that it had one base type that Martin Löw called set. If we, for the moment, stay with Martin Löw, he would put, say that inside set there is a universe that he called U, which is, inductive recursively defined together with the T, the universe a la Tarski. This was Martin Löw's idea. And of course, also Martin Löw had not only one universe, but a whole countable sequence. So for example, we can define in Agda a second universe, U1, which is exactly like the first universe. It's closed under everything. I've only written pi here as an example. But it's also closed. It also contains the first universe and its decoding function. So U is U0. So we have somehow U is in U1. And we could perhaps call this U0. And then, of course, in exactly the same way, we could define U2, U3, etc. So this was Martin Löw's idea of his theory, that there should be a type of sets where all the universes were members. And the reason for this is that when Martin Löw introduced the logical framework, he had a previous formulation of type theory where there was an infinite sequence of universes. And all his operations in that theory had their own variable bindings. And his reason for introducing the logical framework was that in the logical framework, the variable binding should be taken care of once and for all. And so he really thought of set as some kind of meta notion. It was somehow the way in which you internalized the types of the older type theories. So that's the way he looked at it. You should really work completely inside set. And the fact that you up here have function arrows, this should rather be seen as some kind of internalization of the inference rules. So this was not really the function arrow of his type theory, because that existed down here, right, as pi types, or That was his idea. However, when people in Gothenburg started to implement proof systems, they more followed the calculus of constructions idea of universes, that you had the type prop, and then you had some kind of infinite hierarchy of universes. So this was called prop here, right? But we also have, we call it set here. So we have an infinite hierarchy here. And this is like that. When people started programming with this, they didn't do what Martin Löw had told them to do, but they started using these universes up here, and they hardly ever used these except in somehow theoretical lectures, possibly. So all the somehow, you know, the issues about that you sometimes need to have a large type, you make some kind of definition which is not in set, but in use the set itself, so it's in set 1 and occasionally even in set 2, and then maybe you want to do this uniformly, so you have universe polymorphism. I'm running out of time. Yeah, anyway, so you should know this, that this is what you have in Agda, and this is how you program. And Agda, so another thing to say about Agda's universes is that although these are universes a la Russell, they are not cumulative. So in order to go from that universe to that universe, you actually have to invoke a library function. So I won't go into Agda's approach to universes. It's a little ad hoc, but also designed in order to have a good notion of universe polymorphism. But because of the so-called non-cumulativity, it's not entirely satisfactory, perhaps. Anyway, if I now go back to this and talk about the somehow Martin Löw style internalization of universes as particular cases of inductive recursive definitions, then yes, so I think I don't want to run over. I think we should leave it for, let me just say this as the final word, and then I will talk a little bit more about this tomorrow. That, you know, you can obviously define U2, U3, and so on, and you can also observe that the process of adding a new universe to another one is somehow uniform, so it can be internalized. You can define an operation called next universe, which takes a previous universe, think of A as U and B as T, and then build UT for the successor universe. And this is a good inductive recursive definition. And tomorrow I will continue with the story, how do you go to the Marlow universes. And then I will talk about somehow what is behind all of this. Why are all of these kind of things called constructive? What is it somehow that is, behind? Why is it the case that this form of constructivism is all built on inductive and inductive recursive definitions? And this is what we call meaning explanations. And I will implement the meaning explanations in Agda using an inductive recursive family similar to the logical relation that Amal was talking about yesterday. But you have to wait until tomorrow. Okay, let's have coffee.